from Columbia University, and today I'm going to present our recent work on certified concurrent abstraction layers done with my Yale colleagues. So concurrent system software, especially the OS kernel, runs everywhere and form the backbone of today's computing base. So we have to fully trust them, but they are not trustworthy due to program errors. A single program error inside the system might give you a blue screen and fail a presentation, which might not be a big deal. But in some cases, a single program error might kill a human being. Take this Toyota's killer firmware as an example. So in 2013, an unexpected acceleration killed one of its passengers, and this accident was caused by a stack overflow within the assembly module, which is only 350 lines in total. And also, under the investigation, more bugs are found, including potential race condition and potential buffer overflow. So how can we avoid such kind of program errors? Now, many people will stand out, including me and Adam, maybe, to claim that the formal verification is the cure. So we believe that complete formal verification is the only knowing way to guarantee that a system is free of program errors. It sounds really cool, right? But in practice, it's really hard to verify a complex system. Let's take this SL4 as an example. So SL4 is the first verified sequential OS kernel, and it took them 11 years to verify 7,500 lines of C code in their system. Although they have spent that much amount of time to do the work, there are still 1,300 lines of C plus 500 lines of assembly code that are not verified. And especially this assembly code recalls a Toyota accident. A small amount of assembly code might introduce a big problem, so we should not ignore them. But why SL4 didn't verify these assembly modules in their initial version? So the reason might be that there is an abstraction gap between these two languages, between assembly and C. And it's really hard to cover this gap within a single verification framework. But it is pretty common that in a complex system that some modules are written in C, some modules are written in assembly, and some modules are a mix of both C and assembly. And what's more, the language gap might not be the only abstraction gap. Different modules might run on top of different abstraction layers. And these layers might have various features, provide different encapsulations, and the dependency relationships between these modules may also be very complicated. So in order to achieve the modular verification, we really need a systematic way to formally specify these abstraction layers and verify each component at the layer it belongs to. Of course, we also need to take the compiler into account because it might very well introduce bugs. So when take the concurrency into account, things will become much more complicated. So let's assume we run the system on a multi-core CPU, so there might be arbitrary interleaving among the systems running on different CPUs. And if we still want to use fine-grained logs to protect the system, how difficult it will be like to verify it. And also, the multi-core concurrency is not the only concurrency in such a system. There are also multi-threaded concurrency and I/O concurrency. So when these things mix together, many people believe that even it can be verified, the costs will far exceed the sequential ones. So now, let me introduce our new techniques called certified concurrent abstraction layers, which we believe make a big step towards untangling the complexities in this picture. So this give you an example of the certified concurrent abstraction layer. So this is a triple. It says that the module M1 running on top of the layer under the interface L implements the overlay interface L1 on behalf of a CPU or thread I. And these certified concurrent abstraction layers can be composed horizontally like this, and can also be composed vertically like this. So then we introduce concept X, which is extended from ComCert, a certified compiler that can compile the certified C layers into certified assembly layers, and then linked with the manually built assembly layers. So these layers can also be composed in parallel with the layers running on behalf of a disjoint CPU or thread set. So using this approach, we successfully built a certified concurrent OS kernel called Certicos. And we use C layers to verify 6,000 lines of C code, and use assembly layers to verify 400 lines of assembly code, and then use ComCert X to compile and link all the layers together. All the proofs are done inside Coq and are machine checkable. So in the rest of this talk, I will use this example to explain the key concept of our techniques. So this basically is a simple program running over 2 CPUs. And each CPU program will simply invoke the update X method provided by the layer interface L2. And this method trying to add the current CPU ID to the shared variable X. This update is protected by the spin lock and provided by the layer interface L1. And the ticket lock module is implemented using the spin lock module is implemented using the ticket lock algorithm, which you can view it as a ticket machine in the bank. So when you walk in the bank, you get a ticket number, and which is represented by this shared variable T, and then you just wait there until your number gets caught, get served, and this now serving ticket number is represented by this variable N, and all the operations that manipulate N and T are provided by the layer interface L0. So now let's see how we can verify this program. So we borrow some ideas from the game semantics and introduce the so-called strategy to model the semantics of concurrent programs. And we also introduce events to model the operations that are visible to other CPUs and the threads. And then this strategy PI basically defines how the program P will generate events on behalf of CPU I at each step regarding the given log L. And this log is just a list of events. And for example, when we take the ticket number, we will invoke this fetch and increase T method. And the strategy of and this is the atomic method provided by the layer interface L0. And the strategy of this method on behalf of CPU1 simply generates a fetch and increase T event, regardless what the given log L is, and it will also return the ticket number T. This T is fully determined by the number of fetch and increase T events in the logical log. So for example, if there are 2 such events, the strategy will simply append a new one to the log and return 2 as a ticket number. And in other case, if there are 3 such events in the log, the strategy will return 3 as a ticket number. So we can define the layer interface as a set of strategies of the primitives provided by this layer interface, like this. And the semantics of running a module M over this layer interface can also be constructed into a strategy. For example, for this acquire log method, at the beginning it will invoke this fetch and increase T method and store the ticket number into the local variable myT. And then it will get into this while loop to keep queuing the now serving ticket number until it's equal to myT. You can see that we connect the initial state of this getN strategy to all the final states of the previous automation. And the constructed strategy simply keep appending the getN events into the log until the returned now serving ticket number N is equal to myT. And if we are lucky enough to get out of this while loop, we will keep going and generate this hold event to claim that the log was acquired by the CPU I. So this constructed strategy basically defines, given the current log L, how the module MACQ running over the layer interface L0 will generate events on behalf of CPU I at each step. So we can use this way to generate, to construct the strategy of the CPU1. Let's see. It's simply invokes the update X method, and which first try to acquire the lock whose strategy has already been constructed. It will then try to add the current CPU ID to this shared variable X. I mark this step as yellow to note that this step might not be atomic. And then it will release the lock by increase the number of n. And we can use the similar way to construct a strategy for CPU2. And we can view all the CPUs as players in the game. And based upon the strategies, we know at each step how the player will make a move by generating events. So given a hardware scheduler, which is a list of integers, that indicates who will get the turn to make a move at each step. With this hardware scheduler, we can play this game and generate a log like this. So at the beginning, the CPU1 start to make a move and get a ticket with the number 0. And then CPU2 start to make a move and get a ticket with the number 1. And CPU2 trying to then check the now serving ticket number and find that, well, his ticket has not been served yet. So it will remain in the same state. And CPU1 start to execute and successfully get the lock and keep going. And now when CPU2 get a turn to run, it find out it's still not lucky enough to get the lock. So the CPU1 trying to update the shared variable X. As I said, this step is not atomic, so it can be done in multiple steps. Like at the beginning, it will first store the shared variable X into the local register R1, and then switch back to CPU2, and then finish this update by store the registers R1's value plus 1 back to the shared variable X. And then the CPU1 will pass the logs to CPU2 and finish the rest of the execution. You can see that is how we play a game based upon the strategy and generate the log. And we can use these logs to define the behavior of this concurrent program. So we can define the behavior of this program running on over these two CPUs as a set of logs that can be generated by valid hardware schedulers. And then to verify this program, basically is to show that, well, that set of logical logs are captured by this specification, which only consists of 2 logs. The first log is to update the shared X by 2, and then update the X by 1 atomically. And then the second log just do the updates in the reverse order. So from this specification, we can easily derive the property that the final value of this X is equal to 3 if it's initialized as 0. But to prove this program satisfies this specification is pretty hard. We need to first make sure that all the games will eventually terminate, means the liveness property. And we also need to prove the mutual exclusion of this spin lock, meaning that this kind of like update sequences will not be generated by any interleaving. So for example, if the update sequence is like this, the final value of X is equal to 1 instead of 3. So we don't want to do this verification directly on top of this low-level strategies. We want to lift the strategies to some higher level. So to achieve that, let's first focus on the one CPU, and we merge the hardware schedulers with the strategies of other CPUs into a single one called the environment context, and which is specified by the relay conditions. You can view this relay condition as assumptions of the focused CPU over the entire environment. And we use this notation to denote the generated log by running this strategy with the initial log L0 and the environment context E. And then we can define the strategy refinement relation between strategy psi and psi prime. Basically, it says that for any environment context E in the relay condition of psi, there must exist an environment context E prime of psi prime, such that starting from two related initial log, the generated logs can also be related together. So let's do the exercise by lifting this acquire log strategy to a higher level. And the first thing we want to do is trying to prove the liveness by adding this field concept into the strategy. So you can see that now each query to the now serving ticket number will consume some gas, and the strategy will get stuck when it decreases down to 0. And then we need to find a correct initial field value such that the strategy will never get stuck with some proper relay condition. So the first is that if there are some CPUs waiting before CPU I, they will eventually release the log, let's say, within k steps. And if we make this assumption, we also need to add this k field value when CPU I itself acquires the log. And then it's not enough, because if the log holder does not have a chance to get executed, it will also block CPU I. So we have to add this fairness assumption saying that, well, each CPU will be rescheduled within m steps. And finally, we need to guarantee that the CPUs waiting behind the CPU I is bounded, and then we can prove this liveness. But how about mutual exclusion? We find that these relay conditions are still not strong enough. We have to enhance it by adding the constraints that the total number of CPU C is less than 2 to the 32. Otherwise, an integer overflow might lead to a situation such that two different threads get the same ticket number T. So we can do the strategy refinements and lead to give us the definition of certified concurrent abstraction layer, which says that the strategy of running M over L0 refines the higher level strategy phi ACQ. And we can do it in a similar way with release log, and the resulting certified concurrent layers can be composed horizontally like this, and we can then merge these two higher level strategies into a new layer interface L1, and based upon it, we can reason about the strategy of update X to say that, well, it is refined by a higher level atomic update, and introduce a new certified concurrent layer, do a vertical composition like this. And when we try to do the, let's say, the composition in parallel, we have to make sure that the relay condition of each layer is satisfied by the other. And but we know that the relay condition, the only one that's talking about the strategy of other CPUs is this shareholder will release the log eventually. And we have already added a field to it, so we know that, well, it is satisfied. So we can compose these two layers together. So if there are only two CPUs in the system, we can even kind of like merge this environment context into this hardware scheduler. And with this composed certified concurrent layer, we can derive this conclusion that the set of logs running P plus M1 and M2 over L0 is fully captured by the log set by running P directly on top of L2, which is exactly the same with the specification. And so we finish this verification but this only holds if the relay conditions got satisfied, meaning that the hardware schedule is fire and the total number of CPU is less than 2 to the 32. And this is how we do the proofs at the C level. We can also do it at the assembly level with the help of ComCert. So ComCert is a certified compiler that makes sure the compiled code and the source code, the behaviors are consistent. And by adding the layer interfaces to all the intermediate languages of ComCert, we can get this so-called ComCert X that can compile the certified C layers into certified assembly layers. And these certified assembly layers can also be composed horizontally, vertically, and in parallel. In this way, we can verify a concurrent OS kernel. And it takes us more than 17 layers to finish this task. And the whole artifact is evaluated to be functional. Thank you.
We can take a few questions. Let me start off with one. The example code you showed us, I would view as split into concurrency primitives and then the actual operating system parts. Imagine you split out the concurrency primitives from your kernel implementation. I imagine there aren't too many different ones. If you just built those into your framework and didn't try to verify them in a nice modular way, how much easier would the job get, or would it get harder? I'm not sure.
Yes, it's a good question. So from our point of view, so we build that. So let's say we have at the beginning we build this framework. We verify the ticket log, and then let's say we trying to build some other concurrent primitives using the same framework, and let's say we do the MCS log, which can be done almost the same with the ticket log. We find it pretty surprising in the sense that the MCS log is proven to be hard to prove, and we successfully verify it with minimal changes. So we think it might be useful to be generalized. Yeah.
Okay.
Yeah.
Thanks.
Yeah. With this concept of fuel, it looks like you almost have some or can get some performance guarantees. But it also looks like, yeah, the scheduler is a black box. It seems like that these guarantees wouldn't be so useful. So is that something you're interested in, or something that would be useful in this context?
Yeah, thanks, Ian. Yeah, it's a good question. So we are also working on some real-time analysis of this OS kernel, because you can see that once we introduce this field, we can not only reason about the liveness, we might also be able to reason about the, as you said, the performance. But now we are struggling with one thing about the compiler. That's, let's see, if we do the performance analysis over the source code level, how we can get some bounds at the target code level. So we're still unclear about that part.
We could fit in one more question here if anyone has one. Looks like not, so let's thank the speaker again.
Thank you.